Okay, guys, so here we are on the third lecture of the cardiovascular cycle. We talked about the flow, blood flow, factors that affect blood flow, and we talked about the cardiac cycle. Please note that those are mechanical events, and now what we're going to talk about are electrical events. Mechanical means that something is moving, something is flowing. Those are mechanical events. Electrical is just electrical activities, so action potentials moving through the heart. Okay, so that's very important that you understand the difference between electrical and mechanical. Okay, so let's talk about the heart. The heart is autorhythmic, auto as in self, so it sets its own pace. And what we mean by that is that the heart would continue to contract even if you removed it from the body. The nervous system can influence the speed of the contractions, but the heart itself can set the pace. Okay, so for like the Temple of Doom, right? If you take the heart, you scoop it out and hold it up, it would continue to contract even without any neural input at all. So it's different from other types of part in the body. For the skeletal muscles. The skeletal muscles require the nervous system to tell it to contract before it contracts. But the cardiac muscle is autorhythmic. It can contract by itself even if there's no neural input. And that's because about 1% of the cells are what we call pacemaker cells, and they are able to spontaneously depolarize. They can depolarize, become more positive until they reach threshold, and they will spontaneously do so. So let's look at how that looks. So if we're looking at this graph right here, this is just time. This is the membrane potential, similar to what we saw when we talked about neural activity with the action potentials there. But instead of having a flat resting membrane potential, so instead of just hanging out right here at -60, instead what happens is it has these open slow channels, open sodium channels that allow for sodium to just sort of leak into the cell. And as the sodium links into the cell, the charge inside the cell sort of drifts upward until it reaches a threshold. And remember, once you reach threshold, then you're going to cause an action potential. And this is the same action potential that we saw in neurons, or very similar. You have the depolarization phase followed by the repolarization phase. Okay, so you're going to spontaneously depolarize because of those open sodium leakage channels that allow the sodium to sort of trickle in until you reach threshold. Then you're open those voltage-gated sodium channels, and then the voltage-gated potassium channels for the repolarization. Okay, so they don't require the nervous system to contract because they can spontaneously depolarize to cause action potentials themselves. And once you create the action potentials, those action potentials can be propagated or spread, conducted through the other cells, because the cardiac muscle cells have a special type of cell junction where the cells come together that's called a gap junction. We talked about this way at the beginning. A gap junction allows for easy communication between cells. You may have also learned about these in anatomy. These are called the intercalated discs. So these intercalated discs allow electrical impulses, action potentials, to travel directly from one cardiac muscle cell to another cardiac muscle cell. These are not found in skeletal muscles, by the way, and that's how you can create recruitment for skeletal muscles, because you can recruit each motor unit individually. But for cardiac muscle, once you have one cardiac muscle depolarized, all of its neighbors are going to be depolarized as well. Okay, so all of the atria are going to depolarize, and that's going to spread through the atria. Now, separating the atria from the ventricles is a layer of non-conductive tissue, and that makes it so that all of the atria will depolarize and then contract. Wait a second, and then all of the ventricles are going to depolarize and contract. Okay, so it makes it so that both atria contract, and then there's a little tiny pause, and then both ventricles are contract. So I want you to pause right for a second and think about that. Why is it important for all of the atria to finish contracting before the ventricles begin contracting? Okay, so think about it this way. Another way to think about it is what would happen if the atria and the ventricles contracted at the same time, right? So if they both contracted at the same time, you wouldn't create a continuous flow for the blood. So you need the atria to contract, then the ventricles to contract, then the atria to contract, then the ventricles to contract. And that creates a singular direction for the blood to flow through. Okay, if they all contracted at the same time, they would just be sort of squeezing the blood and it wouldn't go anywhere. Okay, let's go on to the ECG, the electrocardiograph. And the electrocardiogram, what that is that measures the sum total of all the electrical activity occurring in the heart. So I want you to notice that it doesn't sort of localize any particular electrical activity, and it's only measuring electrical signals. So it does not measure contractions. So when we think about your heartbeat, and they always show you like the ECG, the heartbeat is sort of inferred that it happens. You can't measure the physical contraction, which would be a mechanical event, with an ECG. But generally speaking, if you depolarize, you're going to contract as well. But you can't measure those contractions directly. It's just looking at electrical activity of the heart, not mechanical contraction. Okay, so let's talk about the different regions of the ECG, learn what happens in each one. So here we have the heart. In the top part of the right atrium, we have a special place, a special location, which is called the SA node, or the sinoatrial node. And in this sinoatrial node, we have a little collection of pacemaker cells. And so the SA node is known as the pacemaker for the entire heart, because these pacemaker cells depolarize at the quickest rate. So even though you have pacemaker cells elsewhere in the heart, these SA node pacemaker cells depolarize the fastest, and so they get to set the rate for the rest of it, because once those pacemaker cells depolarize, the depolarization is going to spread throughout the heart. It'll spread down to the atria, pause a bit, and then down into the ventricles too. So when we look at the ECG, the first region of the ECG is the P wave. And what we're seeing right here is that SA node depolarized spontaneously, and that once it depolarizes, that depolarization is going to spread to all of the other cells next to it. And so the wave of electricity will travel through the cell to cell, all the way through both of the atria, right and left. And so we can kind of summarize all of that electrical activity with depolarization of the atria during the P wave. Now the next piece, see how it says PR segment, note that it is flat. And if it is flat, that means that there are no electrical activities occurring at that time. There's no depolarization and there's no repolarization. So there's no electrical activity. However, there is some mechanical activity. The atria are finishing up their contraction. They actually start during the P wave, but they finish up their contraction before we move on. Okay, so once the wave of depolarization goes through, they will begin to contract. They'll finish up in the PR segment. And then the next thing we have is the QRS complex. Now, please don't break the QRS complex into individual waves. Just treat it as if it's one thing. So it's the QRS complex. Don't tell me about Q, R, and S waves. Okay, QRS complex. During this phase, the electrical activity, the depolarization that spread through the atria, it reaches the AV node, atrioventricular node, which is located right here. And it pauses during the, the PR segment. But at this point, it's going to continue on. So even though the cells are able to depolarize all the ones next to it, the inside of the heart, you have conductive areas that are more conductive than other places. I think of them as sort of like the freeways for the electrical signals. So that wave of electricity is going to spread from the AV node down to the bundle of His, that's the name, the bundle of His, which is located in the interventricular septum right here. It'll go down the bundle of His branches and then up down to the apex, so down the middll, and then it'll go out the outside through the Purkinje fibers. Okay, so from AV node to the bundle of His, down to the apex, and then out through the Purkinje fibers. And so what you can think of all of that wave of depolarization to just sum that all up. Excuse me, that's going to be depolarization of the ventricles. Now, at the same time, and partially the reason why it's so complicated looking, you also have deep repolarization of the atria. So depolarization of the atria happened during the P wave, but during the QRS complex, you're going to repolarize those cells in remember, return to resting membrane potential. That'll happen also at the same time in the QRS complex. So two things happen: depolarization of the ventricles and repolarization of the atria. Okay, so at this point, I hope you can see the pattern. First you depolarize, then you contract, then you repolarize. Okay, so at this point, the ventricles have depolarized. Now we got to contract. Okay, so remember, contraction is a mechanical event, so a physical moving. There is no electrical events during contraction, and so that's why the ST segment is flat. There's no electrical events. Okay, so what happens here is the ventricles, which began to contract during the QRS complex, finish contracting during the ST segment, and now we are on for what's next. You depolarize, you contract, then you repolarize. And so repolarization of the ventricles is going to occur during the T wave. And the only reason the T wave is bigger than the P wave is because the ventricles are bigger. Okay, so I know that feels like a lot of little pieces, but if you remember that atria go before ventricles, and if you remember the pattern, it won't be too hard. You depolarize first, then you contract, then you repolarize. Okay, so the other thing is, remember that they overlap during the QRS complex. And so the QRS complex has two events. We have depolarization of the ventricles and repolarization of the atria. Okay, so P wave, atria depolarize. Then you have the PR segment where the atria finish contracting. Then you have the QRS complex where the ventricles depolarize and the atria repolarize at the same time. Then you have the ST segment where the ventricles finish contracting. Then you have the T wave where the ventricles repolarize, and then you're all set to do it all over again. So you can sort of put the electrical activity and look at it in conjunction with the cardiac cycle, which is all of the mechanical activity. So here we have the P wave here. Once you depolarize, that's going to cause contraction. Remember, systole means contraction. Then you have the depolarization of the ventricles and the repolarization of the atria. After the depolarization of the ventricles, you have contraction of the ventricles, that's systole. And then you have repolarization of the ventricles, that's during the T wave. You can look at, and so when you think about the ECG, sometimes people, when they study the ECG, it's helpful to look at particular, like measure lengths of particular pieces of the ECG. And anytime where you have more than one wave kind of together, more than one region, they're called intervals. Okay, so for example, you have a P wave and you have the QRS complex, but you can have the QT interval because this interval includes multiple regions on the ECG. So If you measure from the start of the Q wave, so from the start of the QRS complex to the end of the T wave, what you're looking at is all of the stuff related to the ventricle. You have depolarization, contraction, and repolarization of the ventricles. So you can say that this QT interval, that approximates the length of ventricular systole, which was the contraction phase of the ventricles, okay? Then we look at the TQ interval. The TQ interval starts after the T wave and goes all the way to before the QRS complex of the next ECG cycle. That would be the TQ interval. And during this one here, this would be diastole, because you're looking at ventricular diastole when the ventricles are just relaxing and filling back up. So you can approximate the two different parts of the cardiac cycle because the QT interval corresponds to ventricular systole and the TQ interval corresponds to ventricular diastole. Oh, one more, R to R interval. So if you measure from the peak of the R to the peak of the next R, what you're looking at is the length of one full complete cycle. Now, I have to mention that the only reason they do R to R instead of Q to Q or P to P or T to T is that the R to R cycle, if you've ever seen like a real ECG like printout, it can be a little messy, but the R peaks are nice and solid to look at. They're nice and big and easy to find. And that's the only reason why they chose R to R interval in comparison to other types of intervals, is because those were just the easiest ones to measure. Okay, so if you measure from the peak of one to the next, that's one full complete cardiac cycle, one beat. So if you look at, you could just as easily gone from the start of P to the start of the next P or the start of Q to the next Q. You would have gotten about the same result. They just chose that because it's the easiest one to identify and see on the physical graphs. Okay, let's relate the ECG to heart sounds. So remember that the lub, remember heart, lub dub, lub dub. The lub is caused by the closing of the AV valves. And remember that the AV valves close because the ventricles contract, which increases the pressure. So you can say that the AV valves close at the start of ventricular systole. And you can say that the dub, which is the semilunar valves closing, they close when the ventricles relax. And so you can say that they approximate the length, the start of the ventricular diastole. Okay, so you have lub first and then the dub. So if you just listen to the heart sounds and you timed the length of those intervals, you could approximate various parts or phases or pieces of the cardiac cycle. So for example, if you went from the lub, remember lub is the start of systole, all the way to the dub, that's going to approximate the length of ventricular systole. Whereas if you went from dub all the way to the next lub, okay, so dub to the next lub over here, that would approximate the length of the diastole or the relaxation phase. You could also go the entire full cycle, so lub to next lub, that would be the full cardiac cycle, or you could just as easily go dub to next dub. Both of those would give you the length of the full cycle. And the reason this is sort of important is because doctors can listen to the heart, and it's really easy to listen to the heart. You don't need, you only need is a stethoscope, and you can make some approximations about the length of times and the health of the cardiac cycle just by listening to the heart. So what I want you to do right now is go into the PowerPoint presentation and watch this video. I really like this video because it takes the ECG and the cardiac cycle and looks at them both at the same time, and that'll help integrate the information for you. Okay, see you later. Go take the quiz now.